Today's topic is going to be on AV over IP technologies and specifically IPMX, which is a new standard for AV over IP. So a quick introduction, my name is Spencer Deem. I'm the marketing manager at Nextera Video, and I'm also here with Jed Deem, the CEO of Nextera Video.
Morning, everybody. To those of you in the Americas anyway, if you're joining us from Europe, good afternoon. Thanks for staying a little late in your evening. And if you're joining us from Asia, thanks even more for getting to us in the middle of the night.
So a quick overview of some of the slides we're going to touch on today. We'll start with an AV over IP introduction, as well as a comparison with some of the current solutions. And then we'll move into the IPMX technology and all of the components required for IPMX. From then we'll review a customer case study. And lastly, we'll have a Q&A. So if you have any questions throughout the presentation, please feel free to drop them in the Q&A box and we'll get to those at the end. At this time, I'm going to launch a quick poll. You'll see it come up now. So give you guys a minute to answer this quick poll and then we'll move forward. Thanks. All right, thanks for your input. So the current AV over IP landscape, we know that there's always an increasing demand for better quality and interoperability in Pro AV. Specifically, we need scalability. So as video frame sizes and frame rates increase from HD to 4K to 8K, and from 60 frames per second to 120 frames per second, we need the connectivity bandwidth between video sources and displays to be able to keep up. So some of the benefits of AV over IP are extended reach, which means we can project long distances over fiber. There's also a significantly lower infrastructure cost, so less cabling and distribution amplifiers, as well as cheaper equipment such as COTS IT switches. And finally, AV over IP has a flexible and scalable workflow for more channels and high resolutions. So some of the current solutions for AV over IP consist of proprietary solutions as well as standards-based solutions. Majority of the current solutions are all proprietary, such as SDVOE from Semtech utilizing the Blue River technology, or NDI from NewTek, and also Dante from Audinate. One of the only standards-based solutions is this new IPMX technology from Ames. So I'm going to launch another quick poll. I'll give you a minute to launch this next one. Okay, great. Thank you all for your input. I'll share the results. So as we can see, most of you are planning on using SMPTE 2110 or IPMX technology for AV over IP, which is great. That's what we anticipated. So moving on, I'm going to pass it off to Jed for an in-depth comparison on the current solutions for AV over IP. Jed?
Yeah, so let's go through this chart. I'll go through this line by line so you can kind of see what these differences are. We've got the main competitors lined up along the top, SDVOE, NDI, Dante, and SMPTE 2110, which is the underlying standard behind IPMX. So we'll talk about it just in the context of 2110. Ethernet interfaces, SDVoE is a 10 gig interface. NDI and Dante are able to do 1G. And 2110 is actually resolution and network speed independent. So it could do 1, 10, 25, 100, or even 2 gig or 5 gig, pretty much anything that you like. From the codec perspective, SDVoE is a proprietary codec developed by the Blue River guys to work a light compression to squeeze 4K into 10 gig. NDI is also proprietary, but it's pretty much a flavor of iframe only MPEG-2. Dante uses a wavelet-based compression, JPEG 2000. SMPTE often works with uncompressed in the broadcast industry, but there is a compressed flavor of it called the 2110-22, and that really works with any standard codec, but the one that's is most highly used today is JPEG XS because of its performance and low latency. As far as data rates for compressed and uncompressed, we'll start with compressed. SDVoE will do 4K P60 compressed, 4K P30 uncompressed. NDI does 4K P60 compressed, but it doesn't support any uncompressed transports. That's primarily because it's often found in software codecs, and it'd be tough for that to keep up with uncompressed. Dante does 4K P60 or 1080p 30 uncompressed, whereas 2110, again, resolution independent, 8K P60 and beyond. It doesn't really care. So for latency, this is an important one. How much delay is there in the hardware end-to-end to compress, transmit, decompress? So for SDVoE, they're running about 8 lines, which is good. NDI, anywhere from 8 lines to a frame. If it's a hardware-based solution, it'll be closer to 8. If it's software, it'll be closer to a frame. Dante is about a frame because JPEG 2000 requires a large vertical aperture. SMPTE 2110, very fast. If it's uncompressed, it's about 2 lines, could be slightly less. And compressed with JPEG XS is about 8 lines as well. So that's really the fastest of the bunch. Another important topic, security and content protection. SDVoE and Dante will pass HDCP, which is a form of content protection encryption, but they don't have any control encryption. NDI doesn't have any content protection, but SMPTE actually using NMOS is able to support full control encryption, which means you've got authorized access lists and you can really control who's doing any kind of switching. On the hardware standpoint, if you want to use SDVoE, you're kind of limited to buying the Blue River chips from Semtech. NDI, again, that could be a core or software. Dante sells modules called Audinate modules. SMPTE 2110 could be done in software, or you could purchase FPGA cores for that. On the control system side, this is another part that kind of adds to the interoperability. So it's not too hard to make a video transport interoperable, but if you want a system to be interoperable, that means your control needs to be common as well. And these first 3 are using proprietary vendor-specific control systems, which is just a lot more difficult to get true interoperability. Whereas 2110 uses NMOS, and NMOS is actually tested interoperable in events that happen twice a year, which Spencer will talk about in a minute. At the end of the day, what we really care about, I think, is quality. Latency is important for many applications, but quality is really the most important. What am I getting, and particularly in an AV environment where I'd like to run over cost-effective networks like 1G? Well, SDVoE, again, does a great job. It is visually lossless. It's less than 2 to 1, but it does require a 10 gig interface. The NDI is a much higher compression. So they're running about 30 to 1 to do 4K on 1 gig, which is visually lossy. You will see artifacts in that. Similarly with Dante. Again, one of the huge advantages of 2110 and IPMX is using this brand new codec called JPEG XS. We're able to run anywhere from 12 to 1 to 15 to 1, and you can get visually lossless over a 1 gig connection, which is really huge.
Thanks, Jed. So why do we need open standards? Well, there's many benefits to having open standards, such as it allows us to leverage the technical expertise of the entire industry, meaning we get peer reviews of significant technologies such as codecs and more. Open standards also allow us to reduce the operational expenses by eliminating complex integration exercises, as well as fostering multi-vendor interoperability and plug-and-play technology adoption. And open standards also avoid intellectual property dead ends that might restrict deployment and market flexibility. So finally, open standards allow us to enable media companies to exploit the economic and performance benefits of large and open markets.
So it sounds like you're saying open standards are a good thing.
Yes, we need open standards. So that being said, what should next generation AV transport look like? In a perfect world, what should an AV transport solution look like? Well, we know it needs to be interoperable. It also needs to be scalable to 8K and 120 frames per second and beyond. We also need it to be resolution and network speed independent, all the way down to 1G, specifically for Pro AV applications. And we need an industry validated codec that's visually lossless with high compression efficiency. And finally, as I mentioned in the previous slide, we need it to be standards based. So what is this IPMX solution? Well, IPMX was proposed by AIMS, the Alliance for IP Media Solutions. And IPMX simply stands for Internet Protocol Media Experience, and it's a new set of open standards and specifications that enable the carriage of compressed and uncompressed video audio metadata over IP networks for Pro AV. So what's some of the technology behind IPMX? IPMX is actually based on SMPTE 2110, which has been designed for high reliability and scalability for use in large systems with thousands of devices. IPMX also uses NMOS for control, which introduces plug-and-play discovery and switching. And finally, IPMX features the JPEG XS compression codec, which is an industry-validated codec. So here we can see the proposed AIMS roadmap for Pro AV. Starting at the beginning here, from a standards perspective, we started with AV over IP with AES 67. And from there, we added 2110 capability, which added video and ancillary data. And you can actually see SMPTE 2110 is actually a subset of standards. So there's all these different components that include audio, video, metadata. And SMPTE 2110 was actually standardized 2 years ago, and it revolutionized the broadcast industry. And in parallel, we've been working on codecs such as JPEG XS, as well as control systems like NMOS, ISO 4 for discovery and registration, as well as ISO 5 for connection management. And these are all part of the required components of IPMX, along with constant bitrate compression from SMPTE 2110-22. Now, IPMX also includes optional components to address specific Pro AV needs, such as HDCP copy protection, general purpose I/O for IR remotes, USB, etc. NMOS ISO 8, which is audio channel mapping, which allows audio channels to be remapped at transmitter or receiver. IPv6 for network addressing, as well as crucial security components such as authentication and encryption, which are not available in other solutions. Another key component of IPMX and 2110 is the timing and synchronization. So this is done through PTP, or Precision Time Protocol, and this specifies timing and latency and enables ultra-low latency and precise synchronization. So SMPTE 2110 actually uses a 2059 PTP, which We have a PTP core that's been developed by Adeus. They've created a white paper, so if you'd like to get more details on the specifics of their 2059 PTP core, please email me for the white paper and I'll be happy to provide it for you. Now, perhaps one of the most important parts of IPMX is this JPEG XS codec. So JPEG XS allows it to be visually lossless in the range of 12:1 to 15:1 compression, enabling 4K P60 over 1 gig networks, which is a huge requirement for the Pro AV industry. JPEG XS is also ultra low latency, so we're talking about just a few video lines. And it's a very small footprint for implementation. So JPEG XS can fit on FPGA cores. For instance, Intipix offers a Tico XS core using JPEG XS. And it can also fit on x86 software codecs or GPU software codecs. Now I'll pass it back to Jed to talk about what NMOS is and how it works.
Yeah, thanks, Spence. The NMOS stands for Network Media Open Specification, which was developed by AMWA, the Advanced Media Workflow Association. And this is essentially the control system for 2110 and IPMX. It was delivered in the form of an open spec, so as opposed to the SMPTE standardization process, which can sometimes be time-consuming, the NMOS process through AMWA has worked as an open specification that's developed in a very agile manner to make it available and be able to do fast innovation and address needs of new markets such as IPMX. Really what it does is it, at the end of the day, enables 2110 based equipment to seamlessly interoperate through vendors, through facilities, through different control panels, really bringing plug and play push button simplicity to video over IP routing. So you can see some pictures on the right hand side here. These are just standard matrix switcher control panels. Could be HDMI matrix or SDI. And in these cases, these panels were all reprogrammed to send NMOS commands instead of SDI or HDMI switching commands. So just like in a typical matrix, you can hit a destination and a source and do a routing through an IP system. So how does NMOS actually work? Well, there's a few components to it, ISO 4 and ISO 5. 4 is the registration and discovery, and 5 is the connection management. But rather than bore you with the specs, I'll just give you an example of how it might work. If we look at the lower left here, we've got a couple sources. These could be cameras, these could be PCs with HDMI outputs feeding some type of converter box, converting it to IP. On the lower right, we've got a destination, which could be a monitor in this case, which is all common, you'd expect it. Our switch in the middle is this icon of a cloud, which means instead of a cross-point switch, it's a IT switch. And there's one new component, which is a registry, which provides a pretty crucial function, which is allowing the plug and play. So step one is the devices power up, and each of these devices sends a IP message to the registry identifying itself. It says, here I am, I'm a camera, I'm camera 1, here's my vendor ID, here's my capabilities. Same thing with the display. So shortly after power up, the registry has a database of all the network devices that are available, which makes it pretty easy for the control panel now. All he has to do is query this registry, and he can even auto-populate sources and destinations. So along comes the user, he pushes a pair of buttons, a source and a destination. What that does, it sends a command to the receiver and tells the receiver to subscribe to this new multicast stream and unsubscribe from this previous multicast stream. And this is done using a technology called IGMP, Internet Group Management Protocol, which is the way you tell an IT switch to allow a multicast stream to pass or not. So really cool system that works quite well and quite efficiently. Now let's talk a little bit about security, because that really is a key component of 2110 and IPMX that doesn't exist in the other offerings. There's really 4 pillars to security in NMOS. The first is confidentiality. We want to make sure that if we're passing data between clients, that it's unreadable to any third party, whether it's control data or anything else. We also need identification. We need to check, have a way to check that the API of a device is interacting with a trusted party. Third is integrity. We need to make it clear that data going to or from a particular API hasn't been tampered with. You might have identified a trusted party, but there could be a man-in-the-middle attack. So that's what integrity protects against. And the fourth is authentication. Just make sure that the packets that are actually coming from an API we're interacting with are coming from who we think they are, and that person is identified and authorized to do such switching or connection. So let's go through an example of how a secure communication system might work. We've got our components, our source at the top, our destination at the bottom, and a controller. This is any type of button panel. But we need a new component. If we want to be truly secure, we add this thing called authentication server, and he holds all the rights and permissions of all the users. So the first step would be the controller would send an authorization request to the server using this technology called OAuth. The server responds, assuming it's a valid user, with a JWT JSON web token. The broadcast controller then uses that token to do what's called an activation, to tell the source to start transmitting. The source just doesn't blindly do it. He now compares that JWT with a public key using the PKI infrastructure to confirm that it is a valid key and it is a valid user asking for this activation. If so, it turns on the essence flow, the flow of video or audio from the source into the switch. It doesn't actually quite make it to the destination yet, because we also need to send an activation to the destination and tell him, I want to connect to this stream that I've just turned on. Well, similarly, the destination is going to check it with a public key, validate that it's an authenticated request, and that it actually connects the stream and allows the content to go from point A to point B. So a very rich security approach to allow high security in video over IP systems. Next, we'll talk about a case study that we did for a customer. We did some work for a customer that does Pro AV control rooms for both commercial and military applications. They had some unique requirements, and we'll talk about how these were met. First is they wanted to have encrypted control. This was met by NMOS. They also wanted to have this authentication server that we just showed to allow different user access levels. That was done with a newer part of NMOS called IS-10. They wanted 4K P60 over 1 gig. That was handled with JPEG XS. And then they also wanted some additional things that kind of went beyond the standards. They wanted an encrypted essence, which is kind of like HDCP, and this we're able to do by extending NMOS with PKI encryption. They wanted a unified routing and moding interface, whereas NMOS is initially deployed just for doing switching. They wanted to be able to do some control over NMOS. Fortunately, our NMOS core is fully extendable, so we were able to add moding to that. They also wanted KVM capabilities for keyboard, video, mouse switching. So indeed, we did some further extension there. Some of these are going to be standardized as part of the IPMX development, but fortunately NMOS is extensible, so if a particular vendor has specific requirements that they want to use in their ecosystem, it's something that is supported. So here's what we ended up with. This is the secure control room. We had some PC sources over here with HDMI outputs that were driving these transmit gateways. There were also some cameras with the SDI outputs driving transmit gateways. These all got pushed onto the 1 gig fabric. And then we had workstations down here for the control room where users were able to, through the receive gateway, they were able to see the HDMI displays from any of these video sources, and they were able to use their keyboard and mouse and control these computers. All under secure control of the system manager, and all optionally encrypted video, audio, USB. At this point, I'll turn it back over to Spencer to talk about our solution.
Thanks. So what is our solution? Well, Nextera and Adeus have combined forces to jointly develop, sell, and support a complete solution for standards-based AV over IP. This includes our the ADAES SMPTE 2110 core RTL and reference design, as well as a fully integrated 2059 PTP core from ADAES, and our Nextera NMOS software consisting of ISO 4, ISO 5, ISO 8, and more. So if you need an FPGA core, why would you choose Nextera? Well, we're a fully modular solution resulting in significantly smaller resource requirements. We're also network speed independent, supporting 1G all the way to 100 gig IP connections. We offer a complete TX and RX reference design, which improves time to market and lowers risk. And we're the only solution with a production-ready 2059 PTP that's fully integrated from ADAES. We also have worldwide support from California, Florida, and the Netherlands, as well as available design services for additional customization of hardware, firmware, or software. And finally, we are certified members of the Xilinx Alliance program and work with most Xilinx FPGAs. So also, we're JTNM tested. The JTNM tested program was developed by the Joint Task Force on Networked Media and was administered by the EBU and IRT. Basically, they developed a thorough test process for validating 2110 and NMOS devices. This consisted of multiple industry interop events in Fox the Woodlands in Texas, as well as Riedel in Germany. And these consisted of rigorous test exercises, and all the successful participants received a JTNM tested badge. So Nextera and ADAES are proud to have received all 5 possible badges with stellar results. And if you'd like to see our results, please check out jtnm.org. So in summary, all the things that we talked about today, the Pro AV market needs high quality, efficient, secure, and interoperable solutions. So IPMX is currently the only solution that provides visually lossless 4K-P60 over 1 gig Ethernet using codecs developed by the best and brightest compression experts. IPMX also includes security for controlling content, like powerful security features such as customizable authorization so that individual users can have different access levels. IPMX also leverages SMPTE, ISO, and AES standards with tested interoperability through the JTNM. And these standards organizations include representatives from major equipment providers, and multi-vendor participation in standard development ensures robustness. So finally, IPMX is the only standard that is not reliant on a single vendor for core technology. Now we also have an AV over IP white paper. This was written and co-authored with Jed, as well as Antoine Hermans, the CTO of ADAES, and Rob Green, Senior Manager for Pro AV and Broadcast at Xilinx. If you'd like to receive our white paper, please feel free to email me at spencer@nexteravideo.com and I'll send it over to you. So feel free to contact us anytime. We're actually offering live demo walkthroughs as well as technical consultations and project reviews. You can contact us at sales@nexteravideo.com. And for all the white papers we have available on AV over IP, as well as the 2059 ADAES white paper, you can email me at spencer@nexteravideo.com. So before we get into the Q&A, I have one final poll for us. Give you a minute to answer this question. Okay, thanks for your participation. I'll share the results. So it looks like our attendees are either not developing products at this time, but they're also the ones that are developing are more likely to develop an IPMX-based product. So with that, thank you for your attention and participation. And now it's time to move on to our Q&A session with Jed.
Okay, we have a couple questions in the Q&A window. If you still have some, please type yours in. I'm sure we'll be able to get to all of them. Let me go through these. So first one, what's the uncompressed latency of SDVOE? SDVOE is able to do uncompressed if it's HD because that fits in 10 gig. I've seen various numbers, anywhere in the range of about 30 to 100 microseconds, which is a few lines of video. So it's hard to really nail that down. I guess it depends on the exact implementation, but it's reasonably fast, so it's a good solution. Again, there's nothing wrong with SDVOE other than it requires a 10 gig interface, so which is just, it's a bit more expensive switches, more expensive SFPs, and a bigger infrastructure to get essentially the same quality you can get with IPMX over 1 gig. Let's see what else we have here. SDVOE supports encryption. Yeah, AES 128 encryption is what's used for HDCP. So yes, SDVOE does support that for encrypting audio and video. Let's see, what size Xilinx chip does the solution require? It's a very compact solution. It'll actually work with any Xilinx device, anywhere from a little Arctics all the way up to the biggest ultra-scale pluses. We've got customers doing as many as 64 TXRXs and some of the larger Xilinx ultra-scale devices. Let's see, is JPEG XS really lossless at 15 to 1? Seems to be pushing it. So there's a difference between lossless and visually lossless. So lossless, it depends on your industry. If you work in the post-production industry, you kind of want it to be mathematically lossless. If you work in the Pro AV industry, or if your users are just looking at computer content or something else, usually visually lossless is sufficient. So it's kind of based on opinions. That's why we gave a range. The Intipix guys claim 12 to 1. They're a little bit more conservative. I've seen tests. I've done a bunch of testing at 14 and 15 to 1. And it's very, very hard to see. I mean, you have to put your nose right up on the display to be able to see any tiny artifact, and they're not objectionable. So it actually works quite well. But the nice thing about JPEG XS is the compression ratio is programmable. So if you can run 2 to 1, 3 to 1, 4 to 1 based on the bandwidth that you have and the type of signal. So if you're just doing HD over 1G, you can obviously do that in a much lower, 2, maybe 3 to 1 if it's 1080p 60, and get a very, very nice image. Let's see, we've got a couple more here. A couple people have asked if the slides will be made available. Yes, they will. We'll send out an email with that information. Here's another one. You mentioned that your FPGA IP cores come with a reference design. What platform does that run on? So we've got a couple different choices. Two different Xilinx boards. One's called a KCU 105, which is a mid-range ultra-scale. KU040 is the chip that's on it. And then we also do a KCU 116, which is an ultra-scale plus that'll handle 25 gig interfaces if you need that. We have a third one that's a 100 gig interface using an Image Matters module. So we've got a few different to choose from if you want to evaluate the system. What else? Is the system available for a demonstration? How does that work? Yeah, so if you'd like to see a demonstration of this, we've got videos of the demo, but we can also provide bit files for the encode solution, encode decode. And so if you get one of those boards I just mentioned, then we can send you the bit file and you can do the evaluation in your own facility. A couple more came in here. So let's see, one of the selling points of the proprietary systems is multiplexing video with audio. Is it easy to implement IP-based AV control system over IPMX? So as far as the multiplexing, one of the nice things about 2110, and which is the foundation of IPMX, is audio and video streams are handled separately as separate multicast transports, unlike some of the other ones where they're all bundled together. So the advantage of that is you could actually send the audio and video to different destinations for different purposes. So you could be looking at the video from one source and the audio from another. Very flexible. And the control system, which is NMOS, fully supports that. So you're able to individually route not only audio and video, but also your ancillary data if you needed to route that to different places. Okay, well, I think that's all the questions. Thank you very much for your participation today. Glad you joined us. And again, here's our contact info if anybody needs to reach out to us. We look forward to hearing from you. Thank you so much, and enjoy the rest of your days or evenings.